So now we will talk about adjoint of a linear operator, of a continuous linear operator in the context of a Hilbert space. So we have already discussed adjoints earlier. This is essentially the same, except that we are now looking at in the view of the Rees representation theorem. You don't have to really go to the dual space. You can work on the base space itself. So that is the idea. So let H be a Hilbert space and let A be a bounded linear operator or continuous linear operator on H. That means it maps H into H. So you fix Y in H and you look at the map X going to Ax comma Y. So this is a continuous linear functional because mod Axy is less than or equal to norm Ax norm Y by the Cauchy-Schwarz inequality, which is of course less than or equal to norm A into norm Y into norm X. Okay, so this is less than some constant times norm X, and therefore this is a continuous linear functional. Consequently, by Rees representation theorem, there exists a unique vector, let me call it A star Y in H, such that you have X A star Y is precisely this linear mapping, that is Axy. So you see this relationship comes in very naturally, and now thanks to the Rees representation theorem we can do it here itself. So it is easy to check that A star is linear. Okay, let us check that itself. So since we are dealing always with complex spaces, it is better to check it once and for all. So let us take X A star alpha X plus beta Y. Okay, so this is equal to Ax alpha Y plus beta Z. That is Ax times alpha Y plus beta Z. That's equal to alpha bar Ax Y plus beta bar Ax Z, which by definition is alpha bar X A star Y plus beta bar X A star Z, and that's equal to X acting on alpha A star plus Y plus beta A star Z, and therefore you have A star of alpha Y plus beta Z is nothing but alpha A star Y plus beta A star Z. Okay, so this is a linear map. It is also continuous because you have norm A star Y. Thanks to this inequality here is less than or equal to norm A times norm Y. So this proves that A star in fact belongs to L of H, and in fact you have norm of A star is less than or equal to norm of A. So A star is called the adjoint map. Okay, so we have the following properties of the adjoint. So proposition H Hilbert and A and AI I equals 1, 2 continuous linear operators on H. okay, then an alpha scalar. So generally complex, so that way, okay, 1 norm A equals norm A star, 2 norm of A star A equals norm A square, 3 A double star equal to A, 4 A1 plus A2 star equals A1 star plus A2 star, 5 A1 A2 star equals A2 star A1 star, and finally 6 alpha A star equals alpha bar A star. So if you have a real scalar, then the conjugate won't appear, it will just be alpha times A. And okay, so let us prove this proposition. So this lists all the important properties, so proof. So we already know that norm of A star is less than or equal to norm of A, already seen. So that is just above, so we have proved that. Now we go back to this relationship with defined A star, so we get AXY equals X A star Y. So mod of AXY is less than or equal to norm X, norm A star, norm Y. So if you take norm of AX is nothing but the sup of mod AXY by norm Y over Y not equal to 0, and that is of course less than or equal to norm of A star, norm of X. And therefore this implies that norm A X by norm X is less than norm of A star, and this implies that norm of A is less than or equal to norm of A star. So we have both the inequalities, and therefore the first one is proved. Okay, so now for the second one. So if X and Y are arbitrary elements of H, you have norm of A star A X inner product Y modulus equals mod AX AY, and that's less than or equal to norm of A square, norm X, norm Y. So norm of A star A is again by the supremum rule, this is less than or equal to norm A square, norm X, and this implies that norm of A star A is less than or equal to norm A square. On the other hand, norm of AX square is AX AX, which is A star A X X, which is less than or equal to norm of A star A, norm X square. So norm of AX square by norm of X square, the supremum gives you norm A square, that's less than or equal to norm of A star A. And therefore once again you have both inequalities, you have that. Okay. Now the remaining are all very trivial consequences. A double star equal to A just comes from this relation itself. This tells you this symmetry in this relationship. You take, you immediately see that A double star is equal to A. Okay, and the fourth one, which is for the sum again, and all these are immediately from the defining relationship. So 2 to 4, 3 to 4, 3 to 6 follow trivially from the defining relation. What is that? X A star Y equals AXY. Okay, so there's really nothing to prove there. It's a very simple exercise. Okay, so if you have a Banach algebra, so remark. So what is a Banach algebra? We have seen this. This is a Banach space in which you can multiply vectors. So you have norm of xy less than or equal to norm x, norm y. So L of any V is a non-linear space. That's typically a Banach algebra, because in addition to addition and scalar multiplication, you all have composition, which is like multiplication of vectors. And you know, if you have two operators, norm of A, norm of T into S, if T and S are continuous linear operators, norm of Ts is less than or equal to norm T into norm S. We know this. So a Banach algebra is okay. So a Banach algebra is said to be a star algebra if there exists a mapping x going to x star satisfying 3 to 6. Okay, and the mapping is called an involution. Okay, if 1 and 2 are also true, also satisfied, then B is called a B star algebra. So thus L of H is a B star algebra with the adjoint mapping being the involution. Okay. So now some terminology, so definition. So H Hilbert space and A in L of H. So A is self-adjoint if A equals A star. A is normal if A star equal to A star A. So self-adjoint is in particular normal, and A is unitary if, so self-adjoint, normal, unitary. It's called a unitary operator if A star equals A star A equals identity. Okay. Okay. So this is the standard definition of this thing. Now example. So M H Hilbert and M a closed subspace. and P from H to M is the orthogonal projection. So that means H is written as the direct sum M direct sum M perp, and then P is from H to M is the orthogonal projection. Okay, so now if you have P star X Y, so if XY belong to H, okay, so this is nothing but X PY. Now Py belongs to M, so what is the characterization? So this is nothing but Px Pm Py. Okay, so it's nothing but Px Py, because that's how the projection is defined, characterized by this. So now Px Py is nothing but Pxy, because again by the repeated application of the definition of the projection, orthogonal projection means this is true, because Px now belongs to M, so Px Py is nothing but Pxy. Okay, so this means that for all x and y this is true, so P equals P star, and of course P is a projection, therefore P equals P square equals P star. So you have this property. Okay, so P is self-adjoint. Conversely, if P equals P square equals P star, then P is an orthogonal projection. So let us take Y belonging to range of P. Okay, so XY is equal to X Py. Y is in the range of P, so XY equals XPY, and that's equal to PXY, because P equals P. So this is because P square equal to P, so XY is same as X equals Pxy. Therefore you have that X minus Px y equal to 0, that is I minus P range is contained in range of P perp. Conversely, if you have you can, I leave it as exercise to you, that if you have range of P perp is in fact equal to range of I minus P. Okay, so therefore you have that H is equal to range of P direct sum range of I minus P. So check, and therefore it is an orthogonal projection. Okay, so example, so let us take ln2. So recall this is Rn with the norm 2. So if you have matrices, then matrices are the same as continuous linear transformations. N by n matrices, okay, on ln2. Okay, and therefore you have that a Hermitian matrix That means A equals the conjugate transpose, matrix is equal to, so this is gives you a self-adjoint operator. Okay, and then the operator defined by a normal matrix gives you a normal operator. And if you have a unitary matrix, then you get the unitary operator. So we are just retaining the terminology of these six. Okay, then final remark. Suppose you have an unbounded operator, so dA contained in H going to H, okay, which is densely defined. Then we can define exactly in the same way A star from dA star contained in H going into H. Okay, and again you have x A star y equals AXY for all x in dA and y in dA star. So leave it to you to check that. Okay, and then all the properties of the adjoint which we have proved earlier are all true. So if you want A is self-adjoint, that means A equals A star. So this should mean you have to prove two things. One, domain of A equals domain of A star, and A equals A star. That means XAY equals AXY for all XY in domain of A. So it is what called a symmetric operator. So symmetric and the domain coincides, then you say that it is a self-adjoint operator. So when you check self-adjoint for unbounded operators, you have to be a little careful. Just checking the symmetry relationship is not enough. We have to also check that the domain of A is the same as the domain of A star.